Perfect. I think everyone's here. So yeah, good afternoon, everybody, and good morning, Maitreyee. So I'm hosting today, just temporarily taking over from Anna while she's on research leave. So we have people from both inside the lab and outside the lab joining. So as Anna has done in the past, I'll give a very quick spiel of an introduction to the seminar series and the lab, and then I will hand over to Dr. Wairagkar to present her research. Okay. So yeah, this is the 24-25 Essex BCI webinar series. Let me move on to the next slide. Yes, I can. Yeah, so the Essex BCI team is, I think we're almost certainly now the largest BCI team in the UK, possibly the largest BCI team in Europe. We specialise in that's the next slide. We specialise in a wide variety of research, including BCI for communication, disorders of consciousness. We work with able-bodied users with applications for human augmentation, learning, memory, neurofeedback, etc. And we also do research in basic neuroscience, machine learning, and related research in signal processing. So we're as a group, we're very interested in a broad range of different BCI topics and related areas of research. Just a quick photo of us, just to introduce us as a group. And one of the things that we're trying to do as we build the group and as we grow is have a series of webinars where we invite prominent and exciting and interesting BCI researchers from all around the world doing a wide variety of different topics and types of research. I'm going to quickly introduce the whole series of webinars because we have a series of these talks throughout the academic year. So we're very pleased that Dr. Wairagkar is joining us today. I'll introduce her in just a minute. Coming up later in the academic year, we have Martin Sieber on the 4th of December. And I realised when I saw this slide, Anna, that actually I used to work with Martin years ago. I thought, he looks familiar. So yeah, very interesting talk. Then we have John Walpole joining in January. And Guillaume Mayer de Olivier Wood from the University of Graz joining in February. So some very interesting talks coming up. And to begin that very interesting series, we are very pleased to welcome Dr. Wairagkar today, who will be giving a talk on high-performance speech neuroprosthesis by decoding intracortical neural activity in people with ALS. So Dr. Wairagkar is a neuroscientist and neuroengineer. She works in advanced neurotechnology and AI. She's currently a postdoctoral scholar at the University of California. So the University of California, Davis, I should say, where she's been working on implanted BCIs for people with severe speech and motor impairments. She did her PhD originally in the University of Reading, which is where I know her from. And going on from there, she worked at Imperial College before moving over to the University of California. So, yeah, back to you. Also, join me in welcoming Dr. Wairagkar to our seminar series. I'll stop sharing my screen now, Maitreyee, and I'll let you begin sharing yours.
Yeah, sure. Okay, can you see my screen?
We can, yes.
All right, great. Thank you for inviting me to present my latest work. And hello, everyone. It is morning here in California, so good afternoon to you all. So I will talk about implanted brain-computer interfaces for restoring speech in people with ALS. Particularly, we have developed intracortical brain-computer interfaces, and we want to restore the lost communication. So a little bit of background about myself. I did my undergrads and PhD in University of Reading in AI and Cybernetics. And I mostly worked on non-invasive BCIs, EEG-based BCIs for identifying movement intention, and also worked on other rehabilitation technologies during my time at Reading. So as Ian mentioned, we overlapped in the early stages of my PhD, and Ian really taught me a lot about BCIs, how to conduct experiments, how to record good quality brain signals. So this is where it all started. Then I did a postdoctoral project in Imperial College London for 3 years. I worked on effective robotics and telemedicine for people with dementia. So I was really working on non-invasive technologies up to this point. And then I moved to University of California, Davis, where now I'm working on implanted BCIs to give higher degrees of freedom to people with paralysis. So let's get started. So it's really important for us to be able to speak and communicate. That really is the key determinant of quality of life. And unfortunately, due to brain injuries and severe diseases, neurodegenerative diseases such as ALS or motor neuron disease, this ability is disrupted. People lose the ability to speak eventually, which can be devastating for their quality of life. So traditionally, people have been using different assistive technologies such as eye tracker and spellers to spell out one character at a time, which are very tedious and slow and tiring. So they are in dire need of a better technology. So BCIs can potentially restore this ability to them. BCIs can decode the brain signals and directly enable them to communicate with other devices. And what better than speech BCI, because speech really provides us a natural and very fast way for communicating. So our aim was to build a BCI that can decode speech from intracortical signals and enable people with ALS to communicate. Okay, so let us look at a little bit of history of intracortical BCIs. And I should mention, we are part of BrainGate Consortium, which is consortium of 4 universities. We have University of California, Davis, Stanford, Brown University, and Emory University in the US. So it's a collaborative effort to advance these implanted BCIs and restore movement and communication in people. So looking at the history of BCIs within BrainGate, we initially had cursor control BCI. So this was again a speller where a paralyzed person could control their cursor and then type out one character at a time. So this gave us a speed of about 8 minutes, 8 words per minute. Then there was more high bandwidth BCI, which was handwriting. So the participant was imagining to write one letter at a time, and that was decoded and printed on the screen. So the participant could communicate by imagining to write one character at a time. So this increased the speed up to 18 words per minute. And then later on, our collaborators worked on a BCI that could decode brain signals into text, which also increased the communication rates further to 62 words per minute. So we wanted to build on top of this groundwork and improve these BCIs and also see how we can make these better and facilitate communication. So we implanted a participant at our UC Davis site. This participant we call T15 is a man in his 40s, is 45 years old, and has ALS or motor neuron disease. He's fully paralyzed. He's severely dysarthric, which means his speech is unintelligible. A layperson cannot understand what he's speaking, so it is very difficult for him to communicate independently. His, of course, language and cognition are all unaffected. And before we started this research, its primary mode of communication was slowly speaking to expert interpreters, which were a couple of people from his care team who could understand him, repeat the same thing again and again. So it was very tiring and very slow process for him to communicate. So our aim was how can we decode his attempted speech and decode that into text and voice that I'll mention later on to restore his communication. So let us look at the example of his speech. Let me know if you hear the voice.
I'm afraid we can't hear the voice, Maitreyee.
Oh, you can't hear the voice? Okay. Let me restart this. I might not have clicked share voice.
Sure.
Okay, there we go. So yeah, the task participant is performing is trying to say the sentence cued to him on the screen. So as you can see, it was pretty hard to understand what he was saying. He speaks very slowly, one word at a time. It is very effortful for him. So our research task was present a sentence on the screen, and when the square turns green, he was asked to attempt to speak it as best as he can in his own pace. Okay, so we implanted 4 Utah arrays or microelectrode arrays. They're very small, 3 millimeter by 3 millimeter. Each array has 64 electrodes, and we targeted 4 areas in speech motor cortex. So this is precentral gyrus. We implanted 1 electrode in ventral 6V. So these are Brodmann areas that we identified, which are hotspots for speech. So we had 4 arrays. Right up top here is 55B, which is known to have some role in preparing the sequences for speech, some higher level preparatory and executionary activity. And then we have premotor areas over here, which are really the last stage before the speech command is sent for execution. So for context, for people who do EEG, this is the area C3 with hand knob that we call hand knob area. And then ventral to that, we have speech motor cortex, and we have 4 arrays there. So we are really looking across the expanse of this precentral gyrus here. So we did human connectome project pipeline scans to identify the areas that were hotspots for speech network. So the yellow areas over here are projection of average human brain on this participant that gave us the locations for where to implant these electrodes. And the next picture is going to be of surgery. So a disclaimer there. Okay, so this is the photo taken during the surgery. These are the 4 Utah implants. You can see that the locations corresponding to these identified areas. Yeah, we had to do open craniotomy and then implant these 4 electrodes in these locations. Of course, there's a lot of vasculature, so you have to be mindful of implanting around that vasculature, and really a lot of planning has gone into conducting and these surgeries. So Dr. David Brandman, who is co-PI of our lab, is a neurosurgeon, and he performed the surgery. So, and I don't have a picture of that, but the idea is that you have these implanted, the skull is placed back on top of this, and these golden wires and then are attached to the pedestals that you saw in the first video, which are percutaneous connectors. And then we plug in the cables on top of that when we record the data. All right. So this is our BCI rig. This is the card. It has multiple computers, some with GPUs, which do this process of signal processing each step in a very modular fashion and give us output in real time. And this is the participant facing card. So this was the screen that the participant sees, and this is the card where the computation happens. So we do this research in participants' home because it is very hard for T15 to travel. He's completely, he cannot move at all. So he's restricted to wheelchairs. So we have to place these research equipments at his home where we conduct our research. And now he's also able to use this on his own. So when we talk speech BCIs, there are two ways in which we can decode the speech from these neural signals. The first way is to decode the text based on what the participant is trying to speak. And the second type is to decode voice directly from these brain signals. And I'm going to talk to you about both of these modalities and what we have achieved with these two types of BCIs. So first I'll talk about brain-to-text BCI. This project was led by Dr. Wairagkar, who is a postdoc in our lab, and this has also been recently published in New England Journal of Medicine. So we are decoding text from neural signals. So first, we ask the participant to attempt to speak the sentence cued on the screen. We extract neural features. So these are broadband activity in the spike band power. So that is very high band activity. So we record signals from 500 hertz to 5,000 hertz. And we look at the average broadband activity in this band and also identify spiking activity, which we call threshold crossings, which are just binary signals, how many times the threshold has crossed a certain level. So using these neural features, we pass them on to a recurrent neural network decoder, which identifies a sequence of phonemes. So at each time step, it identifies how many, what is the most likely phonemes. So in English language, there are 39 phonemes that can form any word that we can speak. So this kind of narrows down the output space. So at each time point, all we have to do is classify between these 39 classes of phonemes. And this is done by recurrent neural network based on the sequence of neural activity that comes in. So in this example, the most probable phonemes here are making the word hello. So of course, we want to form valid words from these sequences of phonemes. So these are continuously fed into a language model. So there are two stages in this language model. The first stage forms words based on these phonemes and keeps updating its predictions as new phonemes come in and as participant speaks further. And then once the participant is done speaking the sentence, it passes on that sequence of phonemes to a large language model. So that language model looks at top 100 candidate sentences that match these phoneme sequences, and then we select the highest ranking sentence. And that is then displayed on the screen and also then played via text-to-speech algorithm in his own voice. So we have created a text-to-speech that sounds like him using the recordings of his speech before he had ALS. So this is how it looks like. At each step, we get different phonemes. The words are formed based on these phonemes, and he's thus able to communicate using brain-to-text BCI. So let us look at the example of a research trial. You'll see that one word appears at a time as he keeps speaking.
No one knows what that is. They have already explored the entire house.
So you can see how this works. It is very highly accurate. So on the very first day of recording, which was the first day we plugged in the cables and recorded his neural signals, we were able to decode his speech with very high accuracy. So on the first day, we restricted ourselves to 50 words vocabulary because we had no prior of how this is going to work. And it gave us very high accuracy. So we measure the accuracy in word error rate, that is the percentage of words that are decoded correctly versus wrong. So lower the word error rate, the better the decoder is. So on the first day, we had word error rate of 1 with 50 words, which is incredible. And if you look at these two horizontal lines here, these are the prior studies that had word error rate of around 25%. That is 1 in 4 words were decoded wrong, which is very difficult to use that BCI for communication. Okay, so looking at the results from the first day, we then expanded the vocabulary to 125,000 words, which is pretty much the entire English vocabulary corpus that a person can use. And then we saw that the word error rate stabilized over the time, and the lowest was again 1%, which means this was very, very accurate brain to text BCI. And then we can see that different locations contribute differently to the decoding, which means that we have complementary information in these areas which contribute to very high accuracy. So I'll point out that this ventralmost array and the dorsalmost array contribute the most to speech decoding. So we expanded the capability of this BCI to enable the participant to use this in his daily life because, saying the research sentences is not very helpful to him. So this is an interface where he is able to speak. It detects when he's speaking, prints out the words on the screen as as the BCI decodes those words. And then after he's done speaking, he clicks on the done button over here. And then further on in the menu, he has options to correct the sentences if the sentence was decoded wrong based on the language model outputs. So in this video, he's talking to his daughter, which has been really transformational for him because he has a very young daughter, and almost for all her life, he has had ALS. So he wasn't able to communicate with her independently. And this BCI really gave him an opportunity to talk to her without having any translators or interpreters.
Hello, my sweet child. Would you like to talk with me? You're a good kid, and I am proud of you.
All right, so you can see how much of an impact this can have on a person's life. And he is using this BCI quite a lot. So we are about 450 days post his implantation. So initially we were doing more research sessions where he was using this BCI with assistance of a researcher. Later on, he started using it in his personal life, which allowed him to continue working, send emails, talk to colleagues, his family, and friends. And now he's using it throughout the day. He is using it about 50 to 80 hours per week. He plugs in, so we trained his family to plug in and start the system for him. So it runs throughout the day. He plugs in around 8, 9 in the morning and then keeps it on till night until he goes to bed. So you can see that his usage has really ramped up. And in this period, he has really used it over 1,700 hours. And now it's even higher because every day we have about 12 hours of new neural data. So yeah, this has really helped him in his personal life. So we also believe that this is the first example of a BCI where we are going beyond research sessions and enabling the participant to use this for his personal use. So he has spoken over 100,000 sentences during this time. And interestingly, his rate of speech has also increased as he's using this BCI more and learning to control it. He started out with 30 words per minute. As you can see in the research sessions, he's saying one word at a time, but over time, he has increased it to 60 words. So that's almost twice as fast as he was able to speak naturally. So yeah, this was brain to text BCI that the participant uses in his daily life, and it has really been transformational for him. What next? What can we do to give more capability to the people who are using these BCIs? Of course, text is not our entire communication. We express via changing our tone, changing our expressions, our cadence, and we change our pitch, volume, etc. So all these biolinguistic features add to the conversation and let us express more naturally. So what we did next was to decode voice directly from the brain signals such that a participant can hear his own voice in real time as he's attempting to speak. Of course, this gives one freedom to speak, make any sounds. So you can say non-word sounds. It synthesizes speech continuously, and importantly, it also gives audio feedback such that you can hear what you're saying, because we are trying to recreate this healthy speech motor loop where we speak, we hear the feedback, we modulate our speech accordingly. So this is what we call a brain to voice BCI. So this is the work that I'm leading and I'm focusing on. So I will talk about what we have done with brain to voice BCI. So the idea is similar. We have arrays implanted in the speech motor cortex of the participant, and he's again attempting to say the sentences displayed on the screen. In this pipeline, again, we extract the same neural features. These are now passed on to a brain-to-voice decoder, which is a transformer decoder that converts these neural features into low-dimensional speech features. So speech is very high-dimensional signals, so we can sample it at 20,000 hertz, 40,000 hertz. And so it's a very high-dimensional signal to directly decode. So what we do is we decode low-dimensional speech features, which are spectral features and pitch features. So we have about 20 features that we decode at each time step using the transformer, and then use a model called vocoder, which translates these low-dimensional signals back to sound waveform that we can hear. So the vocoders are used in voice over IP, so Zoom, etc., which so our computer compresses our speech, sends it on the other end, and then it gets decompressed. That is the same principle here. We decode compressed features, which are decompressed, and then we play them out loud. So all of this happens really, really fast with a latency of just 10 milliseconds. Now, this is important because if you want to recreate the speech motor loop, lower the latency, the better, so that you don't hear an echo or a delay while you speak, because that can be quite disrupting. So our attempt was to run this pipeline continuously every 10 milliseconds, such that every 10 milliseconds we have a new frame of sound. And then we play it back to the participant. So this closes this whole loop. He speaks, we continuously decode the sounds, and then play them back to him in real time. And as opposed to brain to text, this is now a continuous feature space that we are decoding. So it's a continuous sound, which has infinite output space. So this is harder for the decoder to learn the mapping between neural signals and voice in real time. But that also gives us more flexibility in terms of what vocalizations the participant can make. And this work is now available publicly. We have published a preprint, which is now available online. Okay, so let us look at how this works. We have neural signal coming in, and this is a voice that is reconstructed. So at each time step, we have a sliding window, which feeds into the brain-to-voice decoder, which outputs a single frame at a time. So this enables the participant to speak continuously and hear his speech continuously. So one main challenge we have here is since the participant is unable to speak, we do not have a ground truth speech waveform from the participant. So usually when we train supervised machine learning models, we have an output that maps to the input, which is brain signals, and we don't have that mapping in this case. So that is a major challenge to develop a BCI that can output speech continuously. So to tackle that, we generate a time-aligned synthetic speech, which we call target speech, as a proxy to what a participant might have said or how he might have said a particular sentence, and use that to train the decoder. So this is how this is done. So we have text cue displayed on the screen, which we use to generate a synthetic waveform using text-to-speech. With this synthetic voice, we then align that with the brain signal. That is an important step because a waveform that is not aligned with how he's speaking is not useful to us. So we align that with his brain signals, and then we use this time-aligned target voice to train the decoder. So this is his speech waveform while he was speaking a sentence. We then segmented neural activity into syllables. So we have these different syllable boundaries. And based on that, we generate this target speech waveform, which is now if he says something slowly, that word would be stretched to fit his syllable boundaries. And this is how we get one-to-one mapping between a target speech and his neural activity that we use to train this decoder. So let us look at a few examples of how this sounds like. So what you'll hear is the voice synthesized by this brain-to-voice BCI, and he's again attempting to see the sentences displayed on the screen.
This is really very good. I am good. How are you? I know you like it. I love my house.
Okay, so you get the idea. Many of the words are actually intelligible. It's not perfect yet. The speech is a little bit muffled. It's hard to understand, but you can see where this is going. You can understand a few words, and he's able to speak in real time and hear his own voice in real time, which is quite exciting. So you can see this example where we have synthesized speech, which matches very closely with the target speech that it was trained on. And this is very promising. So the correlation between these two synthesized and target speech is very high. It's around close to 90%, which is what we want. Okay, so this framework really allows us to synthesize flexible vocalization. So he can attempt to speak normally, he can mime instead of vocalizing, because eventually people with ALS will lose their ability to vocalize at all. So we wanted to test whether this can also decode speech without any involvement of vocalizations. We have changed the voice of the BCI to match his pre-ALS voice. He can also speak whatever he wants, and also do some other tasks such as say interjections to make his speech more expressive, say non-English pseudo words, so the words, made up words, to test the flexibility of this BCI, and also spell one character at a time. And I'll talk a little bit more about this later, but it also allows him to vocalize expressively such that he can change his intonation to ask a question, emphasize a word, and we also have demonstration of a small singing task. So importantly, this maintains his cadence. So if he speaks fast, it will synthesize the speech fast. If he speaks slow, it will synthesize it to match his cadence. So it is really trying to kind of recreate his natural speech through BCI, and we are also able to decode other features of speech such as loudness, etc. Okay, So let us look at one example where he is miming without vocalizing. And the point here is that you don't notice a difference in the speech output quality. So we want to demonstrate that it is not dependent on his ability to vocalize.
Please. That's no. You have choices.
All right. Now we'll listen to his own voice synthesis where we train this decoder on his pre-ALS voice. So you'll hear a different sound this time.
I hope my nurse is closer. What do you need?
So this allows us to match the voice of the participant. So if we implant this in another participant, we can easily match this to their own voice to restore their speech. So we also tried this while he was saying whatever he wanted. So we asked him to say whatever he wants, and this is what he
I
said.
want to thank you for your eyes. Yes.
All right, so we are now moving towards making this reliable enough for him to use the way he uses brain to text in his personal communication. So that will be our next step to go beyond these research paradigms and try to recreate his speech more reliably using this decoder. So looking at these different tasks, the performance is pretty consistent. As you saw with free response where he's saying whatever he wants, the performance is slightly lower because he uses slightly different strategy that he's gotten used to with his brain to text usage. But otherwise, it's pretty consistent across different activities. And we also asked human listeners to rate the speech. So we played, so for each of the 1,000 sentences that we had in our evaluation set, we asked 15 people to listen to the audio and then identify one of the 6 transcripts that we provided, all of which were of the same length, and the median accuracy was 100%. So given some context, it's the synthesized speech is identifiable. So now that we have demonstrated that we can decode speech and synthesize voice in real time, can we also decode his paralinguistic features and give him more ability to emote through the PCI? So to do that, we gave T15 the ability to change his intonation while he was speaking, emphasize a word, or sing melodies. So this is how it was done. It is the same pipeline as before for synthesizing voice, but on top of that, we had an additional decoder that was identifying his pitch or other paralinguistic features. And based on that, it would modify these features predicted by the original brain-to-voice decoder. So we ran 2 decoders simultaneously. The first one is brain-to-voice, and the other one is paralinguistic decoder that would change the pitch in his voice or change the loudness of his voice. So this is an example where he's saying a sentence as a statement and then the same sentence as a question. And then you can hear the difference in the synthesized voice.
You need help.
So this was a statement.
You need help.
So this was the question. You can see the inflection in his voice at the end of the sentence when he was asking a question. So this is how we did that. We had this secondary decoder that was identifying whether he was changing his intonation, and based on that, modulating the pitch in his predicted brain to voice voice. So we can see here that when he was saying a statement, the pitch in the synthesized voice was pretty constant. So the white trace over here is the pitch contour of the synthesized voice. And during the question, it increased at the end of the sentence. And we got a very good accuracy of over 90% for modulating his voice to ask a question. Next, we gave him the ability to emphasize different words. So he's trying to emphasize the word which is capitalized, and you can hear the difference how this word is synthesized versus when it is emphasized versus when it is not emphasized.
Where are you going? Where are you going?
So you can hear the difference when he was emphasizing where versus when he was emphasizing you. And similarly, you can see that it has higher pitch when he was emphasizing this particular word versus when he was emphasizing this word. So this is pretty compelling example of what we can do with brain to voice BCIs in terms of adding more naturalness and a capability to be more expressive. So this gave us a high accuracy of above 95%. And if you look at the neural data, so this is averaged over several trials, time aligned, and then we have subtracted the general average neural activity to reveal this pattern where whenever he was emphasizing a particular word, so in each row, he is emphasizing the word where you can see a very drastic increase in neural activity, which is easily decodable to enable us to run this paralinguistics decoder. So this is quite encouraging that we can also extract these features from neural activity. And then finally, we wanted to take this a little further and see whether we can identify different levels of pitch. So we designed this short singing task where he was asked to sing a melody, which was presented in this visual form for him to follow that easily. So the melody here is high pitch, mid pitch, low, low, mid, high, and he was supposed to sing that. And then if you look at this bar during the trial, this shows us the decoded pitch level. So we have 3 red lines. This is low pitch, middle pitch, and then high pitch. So keep an eye out on this bar. So initially he will hear the melody prompt, and then when the cue turns green, he will start reproducing that melody.
Me, 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 me.
Me. Me. Me. Me. Me. Me.
So you can see that
No.
I'll stop it. You can see that it was able to decode his pitch and also synthesize that in real time to allow him to sing, quote unquote, sing short melodies. So yeah, you can see that over here as well. High pitch, middle pitch, low, mid, high. And this was the decoded pitch that you saw in the yellow bar during the trial. And if you look at the aggregate decoded pitch, you can see that during different trials, we had different distributions of these pitch levels that was decoded. So that is also quite encouraging. So we can detect not only binary changes in his intonation, but also more finer grained changes in his pitch using the neural activity. So with that, I would like to thank everybody who worked on these projects. It's of course a team effort. This is our lab. These are our PIs, Sergei Stavisky and David Brandman. All right, so that was it. In summary, we were able to decode text and voice from intracortical neural signals, which really enables our participant T15 who has ALS to speak expressively. And we have published this work. The brain-to-text work led by Nick Card has been published in New England Journal of Medicine very recently, and the brain-to-voice work is, the preprint is out, so you can check this out for details. And with that, thank you all, and I'm happy to take questions.
Hey, brilliant. Thank you very much, Maitreyee. Very, very fascinating talk. It's always a shame there isn't a sort of chance to have a round of applause on a Zoom meeting. we can add emojis if that was just done. So yeah, fantastic. Thank you very much. Yeah, questions? Perhaps if you can raise your hand with the Zoom function if you have a question, so we can see who's got questions, please. Okay, Tassos.
Okay, yeah.
Amazing talk. Thank you very much. I'm just wondering, I didn't get the impression that you used the audio information at all. You just relied on the intracortical information. Was that just sort of stick to the one domain, or was it deemed that the voice information wasn't adding anything particularly useful?
So his voice was very unintelligible, which would not have acoustic information to discriminate between different sounds or different phonemes. So we did not rely on that. And importantly, we wanted to make a BCI that is generalizable to people who are paralyzed and can no longer speak. So that is why we relied solely on neural activity, such that eventually, when our participant progresses to the level where he cannot vocalize, it can still work, or can be generalized to people who are in completely locked in stage, who cannot produce any vocalizations at all. And I think I did not mention that, but in his personal use, he has stopped vocalizing because that is very tiring for him. So he just very silently attempts to speak that, and it is able to decode his speech.
Makes sense. Thank you.
Hey, Simis.
Hi. So thank you very much for your talk. You are making us very, very jealous with these results, definitely. So I was wondering mainly about the results you showed for the text recognition. What about any needs of model retraining? Are these results, and especially months after you implanted, with the same model you trained originally, or you need to retrain often or something like that?
Yeah, very good question. So with brain-to-text BCI, of course, with intracortical BCIs, first of all, you can see higher level of instability because the neurons, the tuning of neurons change over time. And the reasons for that are unknown at this moment. So to deal with that non-stationality in the signal, you have to retrain the decoder often. But when the participant is using it daily and continuously, how do we do that? So the way we tackle this question of calibration is that we continuously recalibrate the BCI in the background. So during research tasks, we already know what the ground truth sentence is supposed to be. So we have the text of that. So we recalibrate based on the cued sentence in the research task. And during personal use, if you remember, there were different buttons on the screen for him to choose whether the sentence was 100% correct, whether it was wrong, and if wrong, he was able to correct it. So based on that, all the corrected sentences, we used to retrain that in the background. So there is a decoder calibrator that keeps running in the background, updating after every single sentence he speaks.
Okay, thanks. So it is supervised recalibration, and you exploit instances that you know what he was trying to say. Ian, I'm allowed another 2 short questions?
Yeah.
Maybe. So based on your experience, would you say now that the issue between what is better, decoding phonemes like you did, or decoding semantic information, whole words, is this settled now? Does it look like, if you compare your results with the results of other groups previously, is it better, I guess, to decode phonemes? Is that correct?
Yes, for communication, I think, at least in this use case, it is better to decode phonemes because, of course, we are getting higher classification accuracies. And with phonemes, we have a set of 39 phonemes that we can classify from. So it is a restricted output space, which gives us better reliability. With semantic information, I think that can be a very useful case for people with aphasia, where they are not able to speak the right word, but they know what they want to say. So yeah, there are different use cases. But at this point, I think in terms of accuracy, this is doing much better.
Okay, thank you. And my last question, I have seen previously some work by Bob Knight's group where they were decoding again auditory features like you did in the second part of your work. And actually it was also quite impressive because it was a Pink Floyd song. Which you were here, I think, and the reconstruction was really good from ECOG. So do you have any insights on that? Do we really need implanted microarrays, or the same thing you believe could be done in principle with less invasive approaches?
So with Utah arrays, that is microelectrode arrays implanted in the cortex, they give us very high resolution of information. So we get we get single neuron resolution information, which is really what we want. So we want to get the most that we can with these arrays. There are demonstrations, as you mentioned, with ECOG arrays, which are placed on the surface of the brain. They can also give us substantial information, but it is right now hard to say which one is better. And the study that you are mentioning, they were recreating perceived audio. So it wasn't done on a participant with loss of speech to reproduce that sound. So that was slightly different premise in terms of decoding and their approach. And I think also that was done using some of the arrays in temporal lobe, because that can give them higher signal to noise ratio for auditory perception.
Yes. Okay. Thank you very much.
Yeah, but in terms of synthesizing his voice like we did, I think higher resolution of information is going to help us a lot.
Hey, Alberto, I think you're next.
Yeah, thanks again, Maitreyee, for this presentation. It's an impressive work, as everyone's agree. So I'm just curious about the original frequency range you used. You say you went for very high frequency features, right? Is there any reason why you started on 500? Because coming from people that just does EEG, we're used to the alpha beta ranges. So that's my question.
Yeah, so we have looked at some correlates of speech in lower frequencies. For example, there's beta desynchronization during speech that happens. But to really decode speech or synthesize voice, we need that finer level information, which is present in higher frequency range. So even if you look at the studies where they're doing finger decoding with ECOG, you can see that information in higher gamma power band. With our case, we are looking at spike bar band, which is even higher frequency than high gamma power. So really above 250 or 500 hertz. So that gives us spiking neuron information of spiking or action potentials, which forms a higher resolution picture for us.
Hey, thank you very much. Are there any other questions? Sebastian?
Hi, thanks for the great presentation. So my question is, the whole thing seems to work rather well, and I'm wondering if this was a sort of straightforward process from beginning to end, or whether you tried some things initially that you thought would work and then didn't work at all.
So in terms of brain to text, we had some prior information with our collaborators at Stanford who also did brain to text with their participant. What we learned that more arrays gives us better information. So we decided to implant 4 arrays and turns out 4 arrays are sufficient for decoding text. However, synthesizing voice was never done before. So that was really new paradigm that we explored, and we were able to synthesize voice right from the first day, which was not as high quality as what you heard right now, which improved with as we collected more data, but we were able to implement this pipeline right from the first day. And I think that was one of the new new explorations that we did, so to synthesize voice. And what helped us to recreate this, it wasn't straightforward. Of course, we went through lots of iterations of improvements, the different modules of our pipeline, we iterated through them. And what helped us is we have a simulation pipeline in our lab. So we simulate neural signal based on our own voice, and then use that to test out our models, see how they work, also look at the timings and this whole process, because there are lots of moving parts. We have multiple GPUs running different types of decoders in the background. We have a computer that does this signal processing very, very quickly to extract features from the raw data that is coming in. So there are a lot of moving parts, and we used a simulation of neural signals in real time to test it out. And also we did a lot of offline analysis on the simulated data and some of the publicly available data that we had before. So based on all of that, we were able to do that, right from the beginning. But of course, it went through lots of iterations, and we are still improving. So for example, with adding the emotive aspect of decoding paralinguistic features, that was done much later on, once we knew that we could synthesize his voice. And then we added one feature at a time to kind of increase the degrees of freedom that he can have and increase the control that he can have on the BCI.
Yeah, I think we probably have time for one last quick question. So, Lucas.
Yes, hi, and thank you for your talk. I'm just wondering, you said that the decoder need to be retrained like often. So how long does it take with the patient to get an accurate decoder, actually, each time you visit him, or each time you use the BCI?
Sorry, what was the question?
So you need to recalibrate the decoder with the patient each time you use the BCI, right?
Yes. Yes.
How long does it take to recalibrate it to have an acceptable accuracy?
Yeah. Okay. So I'll start with brain to voice. So these are two independent decoders running two different pipelines. So brain to voice takes longer to train because it is a transformer based decoder. So the recalibration happens after each reset session. It takes about 24 hours for the decoder to recalibrate with the new set of data. And in terms of brain to text, the recalibration happens in the background. So that happens almost in real time. So when the participant is speaking a sentence, it would recalibrate on the previous sentences. So the brain to text decoder keeps up. With brain to voice, it takes about 1 day to recalibrate it with the latest data.
Hey.
Okay, thank you.
Okay, yeah, thank you very much, everybody. Thank you very much, Maitreyee, as well, for a really, really very interesting talk. I'm going to have to wrap up the webinar here, I'm afraid, simply because we're getting to the end of the allocated time, and because I need to leave myself at the time.
Yeah.
I think we're always keen for collaborations and work together. Both within the group and with anyone who's doing anything vaguely related to BCI. So yeah, just like to thank you for the fascinating talk, and just say we are, of course, very, very open to collaborations, as you know from my emails as well. So yeah, please do stay in touch, and I'd like you all to join me in thanking Maitreyee for a really wonderful talk. Thank you very much.
Thank you all for having me.
Much.
Thanks, Ian. And thank you all for great questions. And yes, definitely we can talk offline about collaborations and what can we do together.
Fantastic. Thank you.
Right.
Okay. So, yeah. Thank you all.
Thank you all
very much.
Bye.
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 Thank
Bye.
you.